Now you're all thinking, why do we even learn logs? These seem like one of those just mathemagical things that I'll never use again. Well, the reality is that logs are one of those things that we use quite a bit in higher level math because we are looking for x's in exponents. And most things in the world grow exponentially. Very few things grow linearly. And so exponential growth is something that we see all the time. And oftentimes we're looking for the time or the rate in the exponent. We're looking for something in the exponent rather than looking for something that's not in an exponent. So we need logs to be able to find those. So something like this is really easy. If you think back to our example of trick-or-treating, and you think about the fact that I'm looking for how long it would take me to get 32 pieces of candy, I could say 2 to the x equals 32 or 64, say, and I can say, well, how long will it take for me to get there? And this one's obvious. What does x have to be in this equation? Well, x has to be 6. So we know in this one the x has to be 6 because the exponents have to equal each other. I mean, that makes sense, right? Like 2 to the 6th has to equal 2 to the 6th. It can't equal anything else. It can't equal like 2 to the 7th or 2 to the 8th. Those aren't equal to each other, right? So the exponents have to equal each other. But what about something like this where I say 2 to the 6th equals 4 to the what? And I'm like, what could that be? Well, they don't have a common base right now, so 2 to the 6th equals, well, let's change this into a common base. Can't we change 4 to have 2 as its base? 4 is the same as 2 squared, right? So I could say 2 squared to the x, right? Okay, so then this becomes 2 to the 6th equals 2 to the 2x because remember, our exponent rules tell us that we multiply these two together. So I'm saying, okay, 2 to the 6th equals 2 to the 2x, and now their exponents still have to equal each other, just like they did before. So I say 6 equals 2x, therefore x equals 3. And let's just see if this holds true. If I come back here and I put 3 in, 4 to the 3rd, well, 4 to the 3rd is 64, and 2 to the 6th is also 64, so it does work. It does, in fact, work. So again, you basically need to give them a common base and then set their exponents equal to each other. So what if we did a little bit harder one? These two don't have a common base right now, so I can't just set their exponents equal to each other, but I want to give them a common base. So the question is there a base that I could use for both 1/2 and 4? Is there some number that when I raise it to some exponents that I could get both 1/2 and 4? Well, let's start with 4. 4 is 2 squared, isn't it? So everywhere there's a 4, I could just replace it with 2 squared. What about 1/2? 2 to the what equals 1/2? Well, 2 to the -1, right? So I could replace these with a common base. So instead of 1/2, I'm going to write this as 2 to the -1 to the x plus 7. And this one I'm going to write as 2 squared to the 3x. Okay, now I can go ahead and combine their exponents. So this is 2 to the -x minus 7, because I multiply these two together, and when I multiply x plus 7 times -1, I get -x minus 7. Okay, so 2 to the -x minus 7 equals, and now I multiply these two together, and I get 2 to the 6x. Now I have a common base of 2 and exponents, so I can just set their exponents equal to each other. So I can have -x minus 7 equals 6x. And let's just solve for x. So I'm just going to add x to both sides, and I get -7 equals 7x. So x equals -1. Oh, I wrote 7. I don't know what I was thinking. -1. Okay, so let's check this and let's plug it back in. If I plug this in, does that work? 1/2 to the -1 plus 7 is 6 equals, okay, so that's 1 over 2 to the 6, so that's 64. Okay, and then 4 to the 3 times 1/2. So that's 4 to the negative third. And what's 4 to the negative thirds? Well, it's 1 over 4 to the third, which is 1 over 64. So sure enough, it works.